to you guys another episode of CosmoQuest's Astro 101, where today's topic will be on binary star systems. Before we begin, I want to quickly say thank you. Oh wait, sorry guys, got some other sounds in my ear right now from an advertisement on Twitch. Okay, that's good. Quickly say thank you to Dr. Andres Plazas for a great daily space update. And so, with that said, we're gonna go ahead and just move on into what we're talking about today. So, binary star systems, Joe. When was the last time you talked about binary star systems?
Talked about or heard about? I hear about them all the time because I've heard recent rumors that our own sun may be a part of one. There is some science apparently that has astronomers researching that, which would be crazy, right? Because we can't see another sun close by with our eyes. But anyway, talked about them. I don't think I've ever.
Wait, they're suggesting that our sun is in a binary star system with an
I
with a,
thought maybe I heard uh, it's probably something I'm mixing up on Twitter, but I thought I heard a news story about there being some evidence of our sun being part of a binary system.
that would be
But
interesting. I
that's
don't
like
I don't I don't think I don't think we're a part of a
hella
binary
far
star
away.
system. I think Earth just has one sun. I think we're good on
I
that
may be
point.
making it up completely. I may be making it up completely. It's probably fake news. It's probably fake news.
Probably, more than likely. Um, but yeah, today, guys, we're talking about binary star systems. In the background, I'm showing an image of an artist rendition of a binary star system that has components, two components being both white dwarfs. The idea here with this, or the story behind this particular image, is that the white dwarfs actually might be like kind of rotating around each other to the point where they're going to eventually one day collide into each other and become one, or not become one star, but more than likely undergo an explosion, a supernova. But let me close some of those browser tabs. Am I having issues with buffering? Am I buffering, guys?
Yeah, I'm buffering quite a bit. Can you not see chat again? Is that because
I
I
can
asked?
I can see the chat.
Okay.
I did play around with some of my settings. Hopefully, that is not the cause behind this. Is it better now, guys? Hopefully, it is.
I'm getting like
But hey,
3 to 5 frames a second and buffering, but
oh
I have
no.
started
Hey,
buffering.
Astro, Junichi, welcome to today's stream. So, audio's good, but video's choppy. Um, all right. I hate having to play around with my settings during the middle of the stream. Hey, Adam.
It is coming through at 720p, which is good because last week it was only coming through at 500 something, but
Hmm.
um, the resolution's good, the throughput is not.
I see. Let's try this. All right. You know what? I'm not gonna do anything to the stream. I'm gonna continue, and hopefully, with time, this will improve. But we're gonna continue with the stream, and if it gets bad, then I might just see if I can make some modifications. All right. So, binary star systems. The very first thing we're gonna want to start off with, of course, is trying to understand exactly, well, what are the general dynamics of a binary star system. And so to kind of understand that, and I've used this particular application, this resource, this online resource in the past for past streams. We're going to navigate over to this website that has a nice little simulation, a simulation that we can modify actually to see the dynamics, the general dynamics of a binary star system. With that said, let's go ahead and mosey on over to where that's located. So I'm going to go ahead and change the topic screen here because I need that. Here we go. And in OBS, let's go ahead and do this. There we go. All right. So what we're looking at here, guys, is a 2-star system. The parameters for this particular system we can modify, that being the mass. Upper left-hand corner has some knobs that we can turn to be able to visualize the dynamics, the general dynamics of a binary star system. At the current moment, both components of the star system have the same mass. In this case, 10 units of whatever the mass unit may be. I've lowered the eccentricity to be 0. Note that the eccentricity is basically the shape of the orbits. For an eccentricity of 0, the orbits will look perfectly circular. However, if I change the eccentricity value, you'll begin to notice that the orbits now begin to look less circular and more elliptical. But just for the purposes of this of talking about this concept, I'm going to go ahead and keep the eccentricity at 0. And then there's the last component that you can change, or parameter you can change, which is the inclination of the orbit. Now, the idea here is that at the very bottom of this image, we have our telescope. So that's kind of where we'd be viewing it from. Of course, our perspective is such that we're looking at the star system face on. But if we were in the telescope's perspective, we'd be looking at the star system edge on. And of course, we can change that perspective by changing the inclination angle of the orbit. But right now, just so we can view it, the general dynamics of a binary star system are such that the two components, in this case the 2 stars, orbit the center of mass of the system. Where that's being denoted by this little cross here at the very center of the screen here. There's also 2 plots that we can kind of see at the bottom of the screen on the lower left and the lower right. If you were looking from the perspective of the telescope, given that you're now looking at the system edge on, you'll be able to measure the radial velocity of the 2 components of the star system. So this is the kind of general idea we should have in our head for a binary star system. It's composed of 2 stars. The stars don't necessarily have to have the same mass. You can even change the mass of one of the components. And you can see exactly by changing the mass how that changes the dynamics of the system. But the idea is that you have 2 stars. Both stars orbit a common point in the star system, which is the center of mass of the system. And the key thing you'll notice is that the line going from one star to the other will always cross through the center of mass of the system. Independent of how you play around with the masses or the eccentricity of the system or even the inclination angle, this will always be true. Alright, so with that said, I'm going to go ahead and make sure I'm keeping up with comments here. It's still buffering. This really irks me about this. And I've looked at all sorts of videos to see if I can improve my settings on my computer. Have you guys, at the very least, been able to see my modifications I made to the simulation that's on the screen?
My screen is mostly just a frozen frame.
This is
recently.
This is really
I keep
really
trying to
upsetting.
reload the web page. It's
Alright, you know what I'm going to do? I'm going to keep killing resources because I actually only have 1 browser tab open. Or no, 2 in this case. One being this simulation I'm showing on the screen right now, and the other one being my Chrome web browser showing me Twitch. So I'm going to close that. I've closed out that, and I can still see chat. Hopefully that hasn't went away neither. Okay, I can still see chat. Alright, so we're going to go ahead and move along. And I'm just going to pray that you know, the buffering itself gets better with time. Or goes away completely, altogether if possible. All right. So with that said, we can go ahead and we can move back to the presentation, the PowerPoint presentation itself. And the next logical question that came to my mind, at least when setting up the presentation, was exactly how do we observe these particular star systems? So Joe, have you So I know you told me that you've taken an astronomy course in the past. Did you guys ever talk about binary star systems?
I took Physics 114, which was, I think, the title of the course was Planetary Science.
Ah,
And we started on Earth, and then we talked about the moon, and then we talked about the planets in the solar system, and then we talked about our sun, nearby suns, galaxies, and then the universe. It kind of just blew up like that. We did make it through that HR diagram and that sort of thing, and I don't recall discussing binary star systems
okay.
at all, but I know I've seen them in like documentaries and stuff like that because I've seen all of the documentaries on space.
Okay.
Uh,
Well, that's
but no, I don't think I studied it.
all right. Well, in this case, I hope this information is new and exciting because when I first learned it, it was definitely new and exciting. Um, in fact, my very first internship at Vanderbilt University, it was a part of a REU. REU being short for, it's an abbreviation for Research Experience for Undergraduates. My very first research project for one of these REUs was actually studying binary star systems. Um, and during that experience, I learned that there are primarily three different ways in which you can observe these star systems. And we're actually going to go over those three different ways here today. The very first way, I'm going to go ahead and I'm going to switch back over the view here, is you can visually observe them. And what this means is that you take a telescope, you point it up to the sky, and essentially what you'd end up seeing are two stars. Um, and if you study these stars long enough over time, you will notice that their motions are such that they show to be gravitationally bound to one another. Um, in fact, this is actually a common way of observing binary star systems. In this particular image, I'm showing the Sirius system, Sirius binary visual binary star system, um, where we have two components. We have Sirius A and Sirius B, and if I'm remembering correctly, Sirius A is actually a main sequence star, where Sirius B is a white dwarf star. So another key thing I want to mention about binary star systems is that the two stars don't actually have to be the exact same type of star. Um, like for example, with the Sirius system, we have a main sequence star, and we have which is considered a star that's still alive, and then we have a white dwarf, which is considered to be a dead star. So you can have different combinations of stellar types as a part of these systems. So to quickly make a moment, if you're not buffering, audio is good, so that's the main thing. Yes, seeing no buffering, maybe one frame every 5 seconds. Audio is okay. All right, I'm still seeing people are having a lot of issues with the video, guys, and I apologize for this. Yeah, so Adam is actually bringing up a very good point. So in the case of visual binary star systems, of course, you have to be able to resolve both stars. But what happens if you can't resolve them, right? Um, you get the situation of you just see basically just one star. So we're gonna actually move on to another different way in which these binary star systems are observed. And this particular method of observation is known as, or this particular type of star system is known as a spectroscopic binary star system. Um, Luckily, I was actually able to surf the web and find a nice little image or GIF of what you'd expect to see from a spectroscopic binary. If you have a telescope, you're looking at the star system, and you're able to actually study the spectra from the light coming from the individual components of the star system. So I'm going to go ahead and play the video. And again, I'm praying that I'm just going to leave it on long enough to the point where I hope that you guys will be able to see it. But I'm going to describe what's going on here. So the video is basically showing the center of mass of the system and the fact that we have what appears to be a very large blue star orbiting around the center of mass. On a line directly across from the blue star, that line running through the center of mass, we have another star, much that appears to be a much smaller star orbiting at a farther away distance. But the key thing here is that in this situation, if the stars are very close to one another, the more massive star of the system, and we're just going to go under the assumption that they're both main sequence stars, the more massive star of the system is going to be very bright, very hot and bright, whereas the less massive star of the system is going to be very dim and cool. And so the issue is that more than likely, if you're looking at the star system through a telescope and the two components of the star system are fairly close to one another, you're going to get the situation of you're only going to be able to really resolve one star, that star being the bright star or the primary star of the system. Typically, the primary star of the system is the one that's the brightest. And so, you're looking at the star, you only see one star, but as you begin to look at the spectra, or the spectrum coming from this one star, you're noticing that over time, you're getting different sets of spectral lines, and these spectral lines are moving in a particular way. And if you guys are able to now see the GIF itself in motion, hey Joe, can you guys see the motion of the GIF and stuff like that right now, or is it still?
I just got the GIF on my screen like 5 seconds ago, and it hasn't moved.
Oh my god. Okay, I'm gonna try my best to continue to explain this. So basically, at the very bottom of the screen of the current slide, there is a plot, or there's a graph that's showing the observed spectrum coming from this binary star system. And what we're seeing is two different sets of spectral lines, where one set of spectral lines is denoted as spectral line A, or the spectral line set A, and the other spectral line set is denoted as the spectral line set B. And what you're kind of noticing is that these spectral lines are kind of shifting in time, and that their shifts are correlated with the motions of the individual stars within the system. And so the idea is that as the primary star, the brighter star, as it begins to move towards us, its particular spectral line is undergoing a blue shifting. Whereas for the less massive star, the dimmer star, the one that's unresolvable in the system, we can see its spectral lines though. And what's happening with its spectral lines is that, of course, its spectral lines undergoes a blue shift and red shift relative to its motion relative to us. And so this particular technique is very useful if you're dealing with a binary star system in which you can only resolve one component. I'm going to quickly go to the chat. I'm not really seeing much else. Any other questions coming through here? I will definitely see if I can find a way to fix my settings to the point where I don't have this issue any longer. But the next thing we're going to talk about, of course, is the very last way of being able to detect the binary star system. And this is known, and this particular type of binary star system is known as an eclipsing binary star system. With an eclipsing binary star system, there's one thing that's required in order for you to be able to observe this particular type of star system, or the fact that it's eclipsing. The orbital plane of the star system must be such that it's actually along your line of sight from Earth. or from wherever you're observing the star system from. So the key thing about eclipsing binary star systems, and I'm going to go ahead and this is actually also another GIF. I'm going to play it even though there's been some buffering issues. I'm going to play it. Essentially what's happening here, and I'll describe what's happening. It's basically showing an edge-on view of the star system, where in this case we have two stars. One of the stars is much bigger, which more than likely means it's more luminous, and you have another star that's much smaller, which of course would indicate that it is dimmer than the bigger star. So the bigger stars are going to be our primary component of the star system, and these much smaller, cooler, dimmer star is going to be our secondary component. And basically, we're just seeing the edge-on view of the orbit of these two stars around the center of mass of the system. Now, at the very bottom of this animation, we have a plot. Now, along the y-axis, that would indicate the total brightness of the system, and along the x-axis, we'd have time. So we're able to study the total brightness of the system over time. And what we end up seeing is that most of the time, we're able to see light from both components of the star system. However, there's two key dips in this particular plot, where the plot's commonly referred to as a light curve. There's two key dips in this light curve, where the first big dip that we're seeing corresponds to when the smaller star is eclipsing, or the secondary star is eclipsing the primary star, or the dimmer star is eclipsing the brighter star. And then we have another much smaller dip, which corresponds to when the brighter star is eclipsing the dimmer star. And so these are the three primary means, or the three types of binary star systems that are observed, or three different ways in which you can observe a binary star system. But these particular but binary star systems also are very special, in that their dynamics allow us to be able to do something that we can't easily do with just a single star by itself. We are able to use the dynamics of the star system to be able to determine the masses of its components. So, I'm gonna quickly. Have I been missing any comments here?
No, I think the chat's pretty slow. Haven't been missing much.
Okay. All right, so we're gonna go ahead and move along.
Turned my fan on me and told them that they were welcome for the hissing and the audio instead of me shirtless. That was the two options. Was either my fan noise keying my mic or Joe's boobies. And
yeah, we're gonna go with option A on that one.
The fan noise. And if y'all don't like the fan noise, I'll turn that and my camera off and just get my boobies out. I don't care. It's up to you.
No, please don't do that. Don't forget.
Pretty face, no boobies.
I still have you up on Zoom. Don't
okay.
Don't do that.
Well, that would be the camera I would like to say. Wouldn't have to look at.
Okay. So we're gonna go ahead and we're gonna move along to being able to talk about exactly how would you go about determining the mass of a binary star system. And this is actually a topic that we've discussed in one of my much older streams. So to kind of look at it, we're going to go ahead and bring up another document here. Let's see, where are you? Number 2. Now, I will note, I typically do not go over math in our streams here, but this document it's not bad math. It's actually really friendly math, if you ask me. I thought I would just go over it as something to talk about with these particular types of systems. So, as stated, binary star systems, their dynamics allow us to be able to calculate the masses of their components. In this situation, I presented a problem that I solved, in which we're given specific information that we've been able to observe about a particular star system. In this case, we've been given the angular separation of the star system. That is, if you're looking at the star system angularly, how far apart are they separated? We've been given their orbital period. We've been given their apparent magnitudes in the V band, um, using a V band filter, visual band filter, and let's see. Right, with that information, and we've been given a reference value for the V band magnitude of our star, which is very important for the calculation. And so all that information, of course, is being given here on this line right here. And we can use this information to go ahead and try to determine what the masses of the stars are. Of course, to begin the process, we need to assume an initial mass for the system. So in this situation, the easiest assumption is going to be that we assume that the two masses are equivalent to the mass of our sun. And then we can move along from that assumption and actually apply something that we kind of know is true for stars as well as planets in general. That being Kepler's third law. And so Kepler's third law essentially relates. Actually, all right, Joe, I'm gonna test your science knowledge again. Do you remember what Kepler's third law indicates?
What? Kepler's third?
Kepler's third law.
I can barely remember Newton's third law.
Okay, so
Let's see. So yeah, I don't even know Kepler's first law. I don't think.
let's see. So let's see if chat has the answer for Kepler's third law. The key things that Kepler's third law relates. Okay, so yeah, I'm seeing DPI saying if I'd expect. So basically, yeah, there's crickets in chat right now, right? There's a bunch of crickets
Mostly.
sounding off.
They're getting mad at me for talking about my boobies, but other than that, it's pretty fun.
But yeah, but basically, Kepler's third law relates the orbital period of a body to its orbital separation. In this case, if you were to think about, let's say, for example, yeah, two stars actually. Kepler's third law would relate the orbital period of the stars around the center of mass of the system to their semi-major axis orbital separation to that center of mass. Now, there's also another key thing you have to take into consideration when thinking about Kepler's third law. You also need to know exactly, well, what is the total mass of the system? And so I'm showing here Kepler's third law on this line here, where we have the orbital period of the system denoted by the variable p. That quantity squared is going to be equal to essentially a constant of 4 pi squared in the 4 pi squared times the semi-major axis separation r, that value cubed, all divided by the gravitational constant being multiplied times the total mass of the system. And so we're going to actually use this equation to help us determine what the mass of the system is. But we have to start off with an initial assumption of the fact that the masses of the system are both equivalent to one solar mass. Note, we've been given all the other information essentially though. We know their orbital separation, which we're basically going to get from the orbital separation r, which we basically can then now calculate by taking into consideration, we know the period of the system. We've assumed a mass for the system. So we get an orbital separation, in this case for this particular star system, an orbital separation of almost 18 astronomical units. You can continue from here. Okay, in this particular problem, I also end up calculating the physical distance to the system using the angular separation, the physical separation between the star, angular separation, the physical separation of the star system and their distance. But as of right now, that's unimportant. Knowing the distance to the star system. Actually, no, the distance is important. I'm sorry. The distance is very important because you need to be able to use the distance modulus formula to be able to determine what the absolute magnitudes of the stars are. And so from there, you determine absolute magnitudes for both stars. Moving on from there, you can use the luminosity mass relationship for stars to be able to determine what the physical luminosity of the stars are. You get physical luminosities, and from there you can determine exactly what the mass, or you can get an estimate for the masses of the star. And so the key thing for this is it's actually an algorithm that you'd have to repeat multiple times. You get these masses, and then you return all the way back up to the top, and you rerun everything, but you use the different masses you just calculated. So instead of the masses being equivalent to one solar mass, you'd use the new masses calculated, in this case of 0.92 solar masses and 0.72 solar masses, and you feed it back into this initial formula, and you do everything all over again. And what you'd notice is that as you do this iterative process over and over again, you get new mass calculations for these stars, and eventually those mass calculations will converge. And I know that in in the previous stream I did show exactly how to implement this this algorithm, and basically the end result was that if you notice, the very first run gave us this particular value for the masses of the stars, and then slowly over time the masses well, not slowly, actually quite quickly, the masses began to converge into a single value. And so that's one of the lovely things about these star systems, that they allow you to get masses. And from the masses, of course, you can determine other physical properties like size of the star and stuff like that, and density. And so actually today was a pretty well, there are a few technical difficulties right now, but for the most part, this is a pretty short stream. That's pretty much all I have to talk about as far as binary star systems are concerned. And so now I'm just going to open up the chat for questions.
I would like to say that after the fact, I did finally remember that Kepler's laws all revolved around gravitational influence and like orbital shapes and that sort of thing. But I think, wasn't he the one that talked about how planetary gravitational influence decreases exponentially as distance increases? Is that the same one? For every addition distance, it's that squared in loss of influence.
So Newton's law of gravitation relates the gravitational force to the separation between the two masses that are gravitationally attracting each other. So yeah, Newton's law of gravitation covers that. But yeah,
Kepler. Kepler was the wait. Galileo found the 4 big moons around Jupiter.
Okay.
What was Kepler made famous for? I'm having trouble remembering.
His laws of planetary motion.
Laws of planetary motion. Okay.
Yeah, his laws of planetary motion are they're not exact, but they're good. They're good approximations to exactly how planets move around stars. And of course, Newton's law for gravitation is also very important, but it's a good approximation. But I think it's been superseded, of course, by special relativity, and the results we've gotten from special relativity. Well, not special relativity, general relativity. Excuse me. Wait, do I get credit for knowing that Kepler's law has to do with orbits? Yes, you do.
I already gave him his nerd point.
Okay. But yeah, guys, I again, I apologize for the choppiness of the stream, and I'm gonna see if I can solve this issue. Lately, I've noticed that every time I turn my OBS on, my computer just goes to crap. When OBS is not turned on, my computer runs just fine. So it might just have something to do with like how I've set up OBS. But yeah, Kepler definitely did hit it on the head when, talking about the fact that orbits are elliptical. By any chance, during any point of the stream after, we had our long conversation about it having issues, has it gotten any better? Or is it still like
Not
very
from my
choppy?
point of view. Actually, what I've noticed is it seizes completely for a solid anywhere between 10 seconds and 2 minutes. And then when it finally unseizes, it all very rapidly flies by.
I see. So DPI
And
is saying the
with,
stream is good.
yeah, no, not for me.
Huh. Yes, DPI, you are exactly right. OBS, it kills my computer. I would definitely do that, DPI. It's just that this is the only computer I currently have to work with. I used to work with my other laptop, and that laptop seemed like it was, perfectly okay with the streams. But that laptop's keyboard recently died, so I'm stuck with using and the funny thing about it, another Apple MacBook Pro. It's newer than the laptop I was using previously. They're both MacBook Pros. But yeah. But yeah, guys, if you guys have any questions about binary star systems, we can definitely talk about that, or we can always talk about the conversation that me and Joe were having prior to prior to the stream. But I don't know if that's going to be appropriate for a science stream. Let's see. I'll reset this back to the initial image here. Well, if we're not getting many questions right now, I think I'm going to go ahead and probably end the stream very soon. You are so right, DPI. Newer is not always better. Yeah, I do have an external keyboard and mouse, and whenever I need to grab stuff off of that laptop, I just go ahead and use it. But it's so, I don't know, it feels weird. It feels very weird, using another keyboard. I know I'm essentially just turning my other laptop into like a desktop, doing it like that. Exactly what BigJay just said. We're definitely gonna we're gonna see if we can solve this issue. Because it's upsetting that it messes up all of the animations I've been able to find to help explain some of these concepts. Ooh, chemistry. Sounds like fun. Oh wait, you're formatting a chemistry thesis. So you didn't write the actual thesis. You're formatting it. For a friend, that is. So, Binary star systems are the majority in observable universe, right? Yes, there are lots of binary star systems. Most stars live in binary star systems. So how many binary star systems are of the same spectral class? That answer I actually don't know. I do not want to mess up your name. Clat, I'm just going to go with the first four letters I see there. I don't know. I don't exactly know how many binary star systems are of the same spectral class. If you go under the assumption, thank you, Guido. If you go under the assumption, and this is just me thinking my own thoughts. This is by no means like any like based off of fact anywhere, but if you go off of the assumption that the systems themselves are like born around the same time. Actually, that's a really hard question to even answer for me right now, because I mean, it depends on how much of that gas that was used to form the binary star system, how much of it went into one component versus the other. If they have the same mass, then they'd have the same. You can assume they'd have the same spectral type. But yeah, that's a pretty hard question. I'd have to look that up definitely to answer it. You know how to make it look pretty. Yeah, typically when I had to write my dissertation, I use LaTeX to do it, and LaTeX has a bunch of different options for making documents look pretty. Am I boring Joe to death? I didn't
No,
get.
Joe's terrible sleep and diet are boring Joe to death.
That's a part of the life of working with scientists.
Yeah, at desks, staring at computers for 16 hours straight. You realize you haven't eaten or gotten up in 8.
Yeah, it's a very different life. Like when I was in undergrad, like freshman year, it was Halo all day long almost, except for the occasional time I had to get up and go to class. But Halo. But now it's yeah, like you said, it's crazy hours in front of a computer. You forget to, go grab some food at times. And if you got a family, it's just like, yeah. I can tell you a time when you didn't like it. But guys, definitely thank you guys for hanging out with us today. It's all in Word. Oh man, I couldn't do it. I couldn't do it in Word. I couldn't do a document in Microsoft Word. It just wouldn't work out for me. But guys, thank you for hanging out with us today. We will definitely be back. Yeah, tech is bad. I think it's the best thing to use. But yeah, thank you guys for hanging out with us today. We will definitely be back next Wednesday after Daily Space, which occurs at 12